So far in this course, every chapter has mentioned at least something about plate tectonics, and that pattern will continue for several more chapters. However, Chapter 7 is one that is nearly entirely devoted to plate tectonics. Even photos like this one connect to plate tectonics. My first question would be a review one. Were these features carved by ice or water? How do you know? In this case, there are broad U-shaped valleys with sharp ridges along the valley edges. Now, how did these rocks get to where they are now? Sedimentary rocks are formed at or near sea level, so something had to uplift them. It would be one of the processes associated with plate tectonics. Let's go through some of the history leading to the modern understanding of plate tectonics. To start, you may have noticed that the east and west coastlines around the Atlantic Ocean tend to match up like puzzle pieces. Now, you're not the first to make that observation. People have done so for hundreds of years. Now, the match isn't perfect. In this diagram, the brown shows areas of overlap, and the rose color shows gaps that occur when the continents are pushed back together. If South America and Africa were once together, why isn't the fit of the shapes better? Well, over time erosion happens in some places, while sediments are deposited in others. The shape of the continents was one of the first pieces of evidence used by German meteorologist Alfred Wegener in his development of the hypothesis of continental drift. Continental drift is a precursor to the idea of plate tectonics. One implication of continental drift was that at some point in the geologic past, all land was connected. At the bottom right is Wegener's construction of all land connected as a supercontinent Pangaea. The larger image is a more modern reconstruction. We now know that while most land was connected, East and Southeast Asia were not connected to the rest of Pangaea. This cartoon shows some of the past movements of continents as the supercontinent Pangaea broke up. The first step was a north-south split into Laurasia and Gondwanaland. Next, breakup continues with the shapes of most modern continents becoming apparent. Perhaps the most notable exception is the presence of India as an island in the southern hemisphere. By 50 million years ago, Greenland has separated from North America, and India moves across the equator in its trek toward Asia. Now we can see the modern arrangement of the continents, but we can also look into the future based on the continuation of the current movement patterns. In particular, pay attention to what happens to Los Angeles and the rest of Southern California. Southern California is not part of North America, at least from a geologic perspective. That sliver of lithosphere slides north, and LA's climate becomes similar to that of Alaska. The other major event is that India continues to move north into Asia, making the Himalayan mountains even taller. Now let's review some of the other evidence for continental drift. We've already talked about the fit of the continents on either side of the Atlantic Ocean. Wegener didn't collect fossils, but he did point out their distributions. Mesosaurus was an extinct reptile that lived in coastal and freshwater areas. If South America and Africa were always separated, as shown here, the fossil organism could only occur on one side of the Atlantic. Mesosaurus could not have swam across the ocean. Also, the distribution of the fossils, shown in green, match up when the two continents are pieced back together. Now, these patterns are now known not just for Mesosaurus, but for thousands of species represented as fossils. Additionally, we can do the same matching with major rock formations in the southern hemisphere and mountain ranges in the northern hemisphere. In this case, the Caledonian Mountains of Scandinavia were continuous with the Appalachian Mountains because they were both created during the formation of Pangaea. As the supercontinent broke apart, some of the mountain range went west and some went east. The fourth major piece of evidence were the glacial striations across landmasses in today's southern hemisphere plus India, which spent much of its history south of the equator. Ice sheets have the ice moving away from a central point of accumulation. The resulting glacial striations in their modern position, shown at the top, don't make much sense. However, if the continents were connected, all striations come from a single ice sheet over Antarctica. Now, in spite of all this evidence for continental drift, it was not widely accepted at first. How do you move something the size of a continent? Because there was a lot of evidence, many scientists continued to investigate the idea that continents could move. One of the next steps used paleomagnetism to further document the movement of land masses. The Earth has a magnetic field that, among many other effects, causes magnetic compasses to point toward the magnetic North Pole. That left to right movement of the compass needle is the declination. However, the magnetic North Pole is slightly different from the geographic North Pole. The Earth's magnetic field is three-dimensional, so the needle also tries to move up and down in a compass, meaning the inclination. The inclination will indicate how far north or south of the equator the compass is. Magma contains small grains of magnetic minerals that also rotate in 3 dimensions to record both declination and inclination. And this is locked in permanently when the magma cools and solidifies. Soon after paleomagnetism in rocks could be easily measured, people put together huge amounts of data. The result was a bit of a surprise. Over geologic time, the paleomagnetic data indicated different positions for the magnetic North Pole. This was called polar wandering. However, it wasn't possible to know if the magnetic pole was moving or if the continent was moving. Now, this data was collected based on rocks in Europe, and shortly after, the same paleomagnetic measurements were made in North America. The result was a similar pattern but in different positions. If those positions are adjusted for the combination of North America and Europe together within Pangaea, the placement of the magnetic poles closely match, regardless of which continent you're on. Therefore, the difference was due to continents moving, not the magnetic poles moving. That's why we now call polar wandering the apparent movement of magnetic poles preserved in rocks. Polar wandering was based on data from rocks on land. Harry Hess studied rocks at the seafloor. He observed that rocks from near mid-ocean ridges were always younger than rocks farther away. As a result, he proposed that new seafloor was created at mid-ocean ridges and destroyed at deep ocean trenches. The next step in the study of the seafloor took advantage of some major paleomagnetic changes. Periodically, the Earth's magnetic field reverses completely. For example, a million years ago, a magnetic compass would be pointing toward Antarctica. Now, these major changes in the polarity of the magnetic field are recorded by magnetic minerals in cooling magma. Ships towing an instrument that recorded the direction of the magnetic field found the same pattern of reversals on either side of the mid-ocean ridges. This is because the rocks on both sides of the ridge were being created at the same time. In this cartoon, blue rocks are recording a normal polarity when the magnetic North Pole was in Canada. Red rocks record reverse polarity, with the magnetic North Pole being in Antarctica. All mid-ocean ridges show the same pattern of new rocks being formed and pushed away in both directions. The final step that led to the transformation of the hypothesis of continental drift into the theory of plate tectonics was made possible by the Cold War between the United States and the Soviet Union. Those two superpowers were rushing to make and test nuclear weapons, and at the same time they wanted to monitor the testing done by the other side. To do that, thousands of seismic stations were positioned around the world. Now, by far, most of what they recorded were not nuclear tests, but instead natural earthquakes. These seismic stations recorded the geographic position of the shaking events, which outlined 7 major tectonic plates and several minor ones. The stations also recorded the depth of the focus of each earthquake. This led to the understanding that tectonic plates were composed of lithosphere, the crust and the upper part of the mantle that was cool enough to be a rocky solid. These lithospheric plates moved on the part of the mantle that was deep enough for heat to make it into a pliable, Play-Doh-like layer called the asthenosphere. As I just mentioned, the edges of the tectonic plates were marked by abundant earthquakes, dependent on the type of plate boundary. In divergent boundaries, the plates move away from each other. Convergent boundaries have plates moving toward each other, and transform boundaries have plates moving side by side. Most divergent plate boundaries will occur in the oceans. Remember that oceanic crust is much thinner than continental crust, and lithosphere includes all of the crust. Therefore, it is easier to tear apart oceanic lithosphere than continental lithosphere. Most divergent boundaries will be at mid-ocean ridges. As the plates move away from each other, there are minor earthquakes near the seafloor. Also, magma from the asthenosphere will move up to fill that newly opened void, creating new seafloor. It is possible to form divergent boundaries in continental lithosphere, and the East African Rift Valley is certainly the most famous example. Portions of the plate are pulled away from each other, probably assisted by the upwelling of magma, which heats and softens the lithosphere. As the lithosphere begins to thin, the process speeds up, and eventually a mid-ocean ridge is creating new oceanic rocks. There are 3 options for convergent plate boundaries, determined by what kind of plates are approaching each other. If it is one oceanic and one continental plate, the denser oceanic plate will always be subducted into the asthenosphere. There it will melt, and the magma, less dense than the surrounding rock, will rise up toward the surface and erupt, creating a continental volcanic arc. If there are two oceanic plates coming together, the difference in density is not as much, but it still exists. Oceanic plates are composed dominantly of basalt, which shrinks and becomes denser as it cools over time. Therefore, the older plate is denser and will be subducted under the younger plate. As in the previous slide, the subducted plate melts, the magma rises, and volcanoes are formed. In this case, the line of volcanoes is a volcanic island arc. The final type of convergent boundary occurs when two continental plates move toward each other. Both are much less dense than the asthenosphere, so neither can be subducted. Instead, the rocks are pushed up to make mountain ranges. This is the one type of continental boundary that does not have volcanic activity, although it does experience both very deep and very shallow earthquakes. Transform boundaries are typically very short segments of plates moving side by side. They connect sections of divergent boundaries, which cannot run in straight lines because the Earth is a sphere. There's no volcanic activity at transform boundaries, and the earthquakes are shallow in depth.